We're going to talk about section 7.4, which is powers and roots of complex numbers. Now, we know that when we have a power, let's say we have this complex number 2 plus I squared, that's not really a big deal. We can just set them next to each other and multiply it out with FOIL, and we get 4 plus 4I minus I squared, or plus I squared. So that gives us, this is -1. So that gives us 3 plus 4I. No big deal, right? But what happens if we want to have a power like 2 plus I to the 32nd power? That's a much bigger deal. Trying to multiply it all out like this is going to take a long time. So there was a man named Abraham de Moivre, and he came up with a theorem. And I'm sure there's better ways, people who know languages better, who pronounce it better. But de Moivre's theorem is what we use to do these powers. And what it says is if we have a complex number in polar form, which is why we talked about polar form, we have this complex number in polar form and we raise it to some integer power, our n has to be an integer, then the way we get that is we say our modulus r to that same power times the cosine, and then we multiply the argument. And that gives us our new answer. So we don't have to do it all out like this. So this formula works for integer powers. We'll talk about roots in just a minute. But you need to make sure that you've looked over this. We're not going to prove it. It's kind of beyond our scope right now, but make sure you know this theorem. So let's look at an example. So if we have this complex number, and we want to raise it to the 4th power, well, the first thing we need to do is change this to polar form. So r is the square root of the real part squared plus the imaginary part squared, which is the square root of 52, which simplifies down to 2 on the square root of 13. And our argument, theta, is the inverse tangent of the imaginary part divided by the real part. And we look, this is positive, that means we're in the first quadrant. So when our calculator gives us 1.2898 radians, then we know that we're all right. Now our power here is our n, and that's 4. So what we're trying to do is we're trying to raise this imaginary number to the 4th power. Once we have it in polar form, then we just use de Moivre's theorem. We've got 2 and the square root of 13 to the 4th power. This 4 times our 1.2898 radians. So when we multiply this out, we get 2,704 cis 5.159. Then we can change this back to rectangular form by, here's our r, and we know that a is r times the cosine of theta, and b is r times the sine of theta. We put those up here, we calculate that out, and we get a is 1,168 minus, and b is 2,438.73 I. So if our original question is in rectangular form, then our answer needs to be in rectangular form. But in order to use this theorem, we need to change it to polar form and then back to rectangular form. Otherwise, we won't be able to do the problem. So you need to make sure that you can change back and forth between rectangular and polar form like we talked about in 7.2. and then use this theorem on the polar form to get our answer. Now, we can also use this theorem with roots. This is a corollary to the theorem. We have the polar form, and we are raising it to the 1 over n. Remember, a root, like a square root, is the same thing as to the 1/2 power. A cube root is to the 1/3 power. Well, what we do, again, our n has to be an integer. We have r to that power, 1 over n, and this time we divide instead of multiply. So again, we have to change it into polar form. To be able to use the theorem, but once we have it in polar form, we'll be able to solve that out. So for example, let's say we want to know what the cube root is of this complex number, 2 root 2 plus 2 root 2i. Well, that's the same thing as raising it to the 1/3 power. So we can look at this. It's in rectangular form now. We've got to have it in polar form to use the theorem here. So r is square root of the real part squared plus the imaginary part squared. And we calculate that out and we get 4. And our theta is the inverse tangent of the imaginary part divided by the real part. We look at this and we say, okay, both are positive. We're in the first quadrant. So when our calculator gives us, or when we realize from the unit circle that the answer is pi over 4. So we have our theta is pi over 4, and we have our r is 4. So now we can get this in polar form so that we can use our formula. So what we have is our r times cis of pi over 4 to the 1/3 power. So we use our formula, and that gives us 4 to the 1/3 times the cosine of pi over 4 all over 3 plus I of sine of pi over 4 all over 3. And then we calculate this out. So we have pi over 12, the cosine of pi over 12, and the sine of pi over 12 times the cube root of 4, which gives us, this is our polar form of the root. This is the principal answer. Now, when we have a cube root, it's kind of like when we were finding zeros of polynomials and we knew how many zeros there were going to be by the degree of the polynomial. With the roots, you know how many roots there's going to be by the root, kind of root there is. With a cube root, there's 3 roots. And we can calculate out all of those. We'll do that in just a minute. But this one, first one that we find based on just this initial argument, the principal one, this is our principal answer. Now, if we want to find all the roots, let's try that with this one. So we have the cube root of -1. Well, we know that because it's a cube root, it's got to have 3 roots. So let's get this into form where we can deal with it. Well, it's in rectangular form right now. We've got to have it in polar form to be able to use our formula. So we have our r is the square root of, well, a is -1 and b is 0. So we have a squared plus b squared, so we end up with r is 1. And our theta is the inverse tangent of the imaginary part over the real part. And that gives us the inverse tangent of 0. Well, we know the inverse tangent of 0 is either 0 or pi. And since if we look at our graph here, when we graph this, we're going off to -1. So it's going to be over here. So that means our angle that we're looking for is pi. And that gives us our theta. So we can put this into polar form. And we're looking at, this is the cis of pi, because it's 1 times the cis of pi to the 1/3. And then we have the 1 to the 1/3 power, which is just 1, times the cosine of pi divided by 3, this number down here, plus I times sine of pi divided by 3. And that's going to give us 1/2 plus the square root of 3 over 2i. And that's the principal root. That's the first one we found based on this. Now, because we know there's got to be 3 roots, the roots are equally spaced around the circle. So what we can do is take our all the way around the circle, which is 2 pi, and put it over how many roots we want? 3. This is going to be the spacing between each of the roots. So we have our spacing. So what we do is now we know our next root is going to be the cosine of pi over 3 plus 2 pi over 3 plus I times the sine of pi over 3 plus 2 pi over 3. And this gives us the cosine of pi, which is -1, and the sine of pi, which is 0, so that just gives us -1, which we really should have known already. And then we know we need 3 roots because it's a cube root. So we add it one more time. So we have pi over 3 plus 2 pi over 3 plus 2 pi over 3 plus I times the sine of pi over 3 plus 2 pi over 3 plus 2 pi over 3. So that gives us 5 pi over 3, and the cosine of 5 pi over 3 is 1/2, and the sine is negative square root of 3 over 2i. So there's our 3 roots. When you have a cube root, we want 3 roots. If we have a 4th root, then we're going to have 4 roots, or 5th root, we're going to have 5 roots, and so on and so forth, so that we can figure out how many we have. So we figure out our spacing, start with our principal one, and then add the spacing however many times we need to add it, 1, 2, so that we end up with the right number of roots. If you're in degrees, of course, you would take 360 degrees and divide it by how many? In this case, it's 3. So you divide by the number of roots. And so this, we know it's a cube root, so it's going to be 3. So that gives us all 3 roots. Make sure you've read this section so that we can go over it in class.